All right, guys. Sorry for late video. I've been mentioning on my other videos. We're trying to get one tutorial done a week. If not, it will get rolled over. Best thing to do is just kind of look at the YouTube channel and see what's happening. In the case of this class, if a geometry video just finished, then the Algebra 2 video will come next. So let's get into this. So we're going to be talking about key features of logarithm and piecewise functions. Logarithmic functions, we just talked about it in the last one, where um, it's the opposite of exponentials. Exponentials never touch zero; they just keep going on forever and growing. Logarithms are the opposite, so they or let me kind of draw it out again. So if you have an exponential, logarithms are the x and y reverse. So if this is x equals 0, then the x-axis basically. Then you also have the y equals 0, the y-axis, right? Let's pretend I drew that straight, which means this function, it will go down and down forever, but never touch 0. But at the same time, it will keep climbing up forever and ever and ever, going on to x equals infinity. And this one over here, the original exponential function, this one climbs all the way up forever and ever and ever that way too. So they're both climbing up. Or this one, yeah, they both climb up. This one is just growing to x equals infinity faster. This one's growing to y equals infinity faster. This one never touches y equals 0. The blue one never touches that. They're literally the same thing, just with the x's and y's flipped. So this is an exponential, some number to the x power. This is it flipped. It would be the logarithm, log base of whatever that n is on this side. And technically it's to a y value. So that's the difference between these. We're going to be talking about the key features of piecewise functions are just a bunch of different functions that kind of start and stop at different points. And you'll see what I mean. All right, so let's get into that. So in the objective for this lesson, we're going to interpret features of logarithmic functions and piecewise functions. And we're going to do it with tables, graphs, and the equations. So the tough part here is usually the tables. A lot of students have trouble understanding the table. I'll do my best to explain it. Graphs, we just look at it and grab the numbers from it. Equations, what we're going to do is we're going to be looking at the parts of an equation. For example, if I have like log 3 of y or whatever, and we add like a 2, we're going to see how my graph changes based on that random change by just adding the 2. So we're going to talk about those and how they change doing this. We've done stuff like this when we did transformations. So anytime we've done transformations, we're like, oh, if you add it to the x, it moves it to the left. If you add it to the y, it moves it up. If you subtract it from the x, it moves it to the right. Those fun stuff. So let's kind of talk about behaviors. So what we're going to do here is using a calculator, find the functions of log x. All right, so what I'm going to do here is I'm going to grab Desmos real quick. And I'm going to go to the scientific calculator. And what we're going to do here is we're going to type in the function log of x. So log of whatever I want to plug in. So I put parentheses there because I don't know what my x is. So this one, it's telling me to plug in a -1. I plug in a -1. And it says undefined. Now what that means is in a log function, remember I said it never touches, gets past 0? Well, that means it can never be negative. It can be very, very close to 0. It can't be 0 and it can't be negative. So what I'm going to say here is I have to write down, it has to be undefined. Now let's try the 0. Now, as I mentioned before, it gets really, really close to 0, but never touches 0. So it'll still be undefined. And I'm going to write undefined. It doesn't exist because it can't happen. And the reason why it can't happen is because let's talk about our exponents. So an exponential, x to some power, equals y. Remember how I said in a graph, this can never be negative. And the reason why it can never be negative is because this power, we're saying 10 to the x. When we're talking about log, we're talking about the opposite of 10 to the x. There's an invisible 10 here. This can never be negative because even if we do like a negative power, let's say we do 10 to the negative 2, well, all this means the negative exponent flips it over and we get 10 to the second, which is 1 over 100. There's no way this can ever be negative by multiplying. There's some log functions that are always negative or they switch back and forth. And it's usually when you do like log of negative something, but even then, that negative changes a little bit. That's a little more complicated. We're not going to be talking about those. For all intents and purposes, logs just can't be negative unless something forces it to be that way, like changing the x or something. So now we're going to do log of 1. So let's do log of 1. And that's 0. So basically, when our x value is 1, our y value is 0. So I mentioned how it's basically like we're flipping it, and think of it logically. So let's say we had 10 to the 0, we would get 1. So I know I'm covering a lot, and I'm sorry, but this is just to kind of give you like a visual representation as to why that's happening. All right, so this is going to be 0. And now I'm going to plug in 2. Now, it's really hard to kind of mathematically prove why it's this fraction. I can't give you like a reason that's, how many spaces do they want us to do? What do you think? Okay, I'm going to do 3 decimal places because they haven't given me any parameters. So I'll just do that. There's no real reason on why it equals that because remember, log is log base 10. So if we do 10 to some power, how do we get 2? Well, that's going to be 10 to 0.301. It's not even 10 times itself one time. It's 10 times some part of itself is going to give us 2. And then they're going to talk about 3. So let's plug in a 3. So I'm going to plug in a 3 in here. And we get, oops, I didn't mean to hit enter, 0.477. So I get 0.477. And then I'm going to do the 5. So I'm going to do 0.69, and this will round up because of this 9 right here, 0.699. 0.699. And they want us to do 10. Well, this should be 1 because think about it logically. 10 to what power gives us 10? 1. So let me go in here and I'm going to plug in 10 and I get 1. That's important to note that some people think that this should be 0.5. It's not 0.5. We're not multiplying. This isn't multiplication. It's multiplying by itself. So that's why we get this weird number right here to end up giving it 5. This one's simple. So if we're thinking about this, again, logically, 10 to what power gives us 100? 2. So that should be 2. So if I do log of 100, I should get 2. So let's try to let's look at this again. 2. So what's happening here is this can grow a lot, but this is going to grow very, very little. Oops, this was supposed to be 1. This is going to grow very little over time. So let's talk about the other questions it was asking. It was asking, what do you think the domain should be? Well, I can see here that the domain is x is bigger than 0. X is greater than 0. Because 0 doesn't work, but the other numbers do. Now, when it's talking about the range is, if you look here, we have fractions here. We didn't get into negative numbers. So uh, it looks like there's no real numbers, but there are. It's just we never entered a fraction in here. If we would have entered some kind of fraction in here, we would have gotten negative numbers. Like let's say I say 0.01, you see that there's a -2 there. And the reason for this is like 0.01 is the same thing as this is a 1 in the hundredth place. How do I get 10 to be that? It's like, well, first I want the fraction to be at the bottom. And then 10 times 10 is 100. So it's 1 over 10 to the second. So that's how we get this -2 there. So it is possible for it to be negatives, is all real numbers. All numbers that we can think about should fit in the range for the y value. Again, I know it's a little confusing because I said that the x and the y kind of flip flop, but you just have to think if it was an x or if it was a y for an exponential, that means it's going to be an x for this. So it's all real numbers, and it's asking what do we think about the n behaviors? Okay, so n behaviors, it's like for the n behaviors going to the left, x cannot be negative, and y can go to negative infinity. This is just the idea that y can all y's can work, going all the way down to negative infinity. This x has a cutoff right there. Going to the right, x can be infinity, but it gets there slowly. Well, the y gets there slowly. I'm sorry. X can't really go slow or fast because it's our independent variable. So X is going at a normal rate, but we notice that the Y starts slowly growing. It's still growing, but very, very slowly. That was a mistake right there. Um, so so when we're going to the right is the same thing as x is approaching infinity, and you'll get used to that language later. X and y can be infinity. X and y can be infinity. Uh, The y grows slowly, though. You don't even have to write that part. The y grows slowly. So something like that, just talking about it. We can see here how they're talking about how it goes into positive infinity and things like that. But make the language your own to understand it as best you can. I cannot stress enough how much I do recommend these videos, especially if you're having a hard time understanding me. They do kind of, I think, break it down really well. It's one of the things that I think Edmentum does pretty good is when they actually have videos instead of putting all this information on screen that kind of overwhelms people. All right, so when we're talking about logarithmic functions, properties. So the word properties when we're talking about logs are these ideas here that log any base, any number base log, if it's 1, it has to be 0. If the base is equal to itself, it's always going to have to be 1. If you have a base to itself and it has an exponent, then this answers that exponent. And that makes sense because obviously log to what base is going to give us this, the x equals x, obviously. Because it's like, well, what do I need to become this? X. What does this x need to be this? And again, if you're having trouble with this, I do recommend studying up on logs. You can rewatch the log video if that helps. I'm not sure why this is not erasing. That's really weird. All right, so again, and you can watch the other properties as well. So let's kind of move on here. All right, so a parent graph of a log function. So a parent graph is just the basic idea. I've drawn it several times. You've seen me go like, oh, a parent graph is, and it's kind of weird because they do a picture of an exponential. The parent graph of a log function is always this. It's always never touching the x-axis, and or never touches the y-axis, and it crosses the x-axis right here. All right. So going on to the next one. Oh, and key features. Key features, when they talk about key features of a logarithm, they're talking about, let me show you here. They're talking about where the asymptote is. So sometimes we do change this asymptote. This is only a parent function that the asymptote where the graph never touches. So the graph, oh, this looks terrible because of that other graph in the back. So sometimes graph asymptotes change. So there's times where it doesn't touch changes and where it crosses the x-axis changes. Those are a few of the key features of a logarithm. So we're going to be talking about those right here in this activity. So let's go to here. So we're going to graph a log function. So in this activity, we're going to graph logarithmic functions. Read the directions for each question. We're going to graph this. And remember, if there's no base, it's log base 10. So in order to graph, you're going to go to relationship because the function is a relationship. You can do logarithm. These features are cool, but it takes a deep understanding of it. So if you do logarithm, you have to make sure your base is 10. So that's one of the reasons I don't like this is if you want a log, this is log base 10. So usually what I recommend is, and I can show you that this is right now. So log of x. So here's the function. But if I would have done logarithm, it might have taken me a while to understand that this is log base 10. A is a number in front of it. So since this has no coefficient, no number in front of it. That's why we put the 1, because there's that invisible, it's being multiplied by an invisible 1. All right. So that's why I usually recommend just go into custom. The relationship one I think is good for when they give you like a little task, like, hey, try to line these up or try to move these. I think those are really good to play around with this. So here's our graph. And this is asking us, examine in part A our x-intercepts. So the graph has no y-intercept. So if we look at the graph, it never touches the x-axis. It goes along, or it never touches the y-axis. I keep saying those incorrectly. I mean, it never touches this. It never touches the y-axis. So there can't be a y-intercept because it never touches the y-axis. And then if we look here, right here, it does cross the x-axis at 1. So the x-intercept is 0 comma 1. So the x-intercept is 1. It crosses the y-intercept. The x-intercept, and it's important to remember the x-intercept isn't just the x value, it's a point. So the x-intercept is 0 comma 1. A point has an x and a y value. If I were to say x equals 1, that's not correct because x equals 1 is a line. It's this dotted line that I put right here, which I probably should have used another color. It's this line. That's x equals 1. So you want to say the x-intercept is 0, 1. It's the point where it crosses the x-axis. It's saying what is for this tutorial, I'm just going to refer to end behavior as it does want it as x approaches positive and negative infinity. Okay, so when x approaches negative infinity, it's talking about as we go to the left. When x approaches positive infinity, it's talking about going to the right. So that's what I'm going to mean. We're going to be talking about the y value as we go to the left and the x value, or the y values, because when we're talking about graphs, we're seeing how the x's affect a y. So we don't necessarily care about the x's, they just kind of tell us where these y behaviors are happening. So we'll get to that in a bit. So the asymptote. So since the graph never touches the y-axis, the asymptote is x equals 0. And in this case, I am correct in saying that because it's never going to touch this line. This line straight here. The y-axis is known as x equals 0. End behavior. Um, there is no negative domain. So the x value is never negative. So as x gets closer to 0, y gets closer to negative infinity. As x gets closer to infinity, y gets closer to infinity. So even though y does get closer to infinity much slower than x, like here we're going up 1 and x and y still isn't at 1, it's still going to infinity. It's just going to get there slower. And infinity really isn't an actual number, but it's important to say that. So I don't like this end behavior thing because you kind of have to know the domain and range before that. So they put this in a very weird order. So I'm sorry for the numbers. I have like a gaming mouse, and every time I squeeze my mouse a little bit, you'll see me randomly push these numbers. And I guess I guess if I push 11, it's a minus sign, and if I push 12 on my mouse, it's an equal sign. Those are interesting to know. Anyways, just so you can kind of understand why there's random numbers there. So the domain. So the domain is x is greater than 0. X is bigger than 0. The alligator wants to eat the x. And the range is all real numbers. All real numbers. So if you look at that, it's going to equal all the numbers. So they kind of show you here. They show you in what's known as interval notation, meaning that it starts at 0 and goes to infinity for the domain. For infinity, it's like negative infinity all the way to positive infinity. They kind of show it as rapidly. I guess that would have been a better way for me to describe it. Is the function is growing fast and it's growing slow. Oh, I never wrote if it was also determined if it's increasing or decreasing. I think that's kind of goes without saying, like, as x goes to infinity, so does y. That means it's growing. So, but I should have done this. So as we go to the left, it's decreasing. As we go to the right, it's increasing. So as we're going to the left, we're decreasing fast. As we go to the right, it's increasing slow. All right, so let's look at this other graph. So now we're going to do ln of x. And if in case you don't know, ln of x is the same thing as log base e of x. E is this number that occurs naturally in math, like a bunch of scientists and mathematicians got together and realized that this number occurs a lot, so it is a number worth pointing out. So if we look at this relationship, I'm going to type in custom uh, ln of x. And you can see that it stopped being italicized when I typed in ln because it's like, oh, you're talking about the function ln of x, which is right here also if you need it. So it's like, oh, if you're talking about the function, then yeah. So if we look here, it's like, wait a minute, this has the exact same information. So examine the key features of this. So we're going to say that it has a lot of the same. So most of this information, actually all of the information is going to be exactly the same. So it's a little lazy, but all the questions are exactly the same. The only thing I'm going to add to it, since I forgot to add it in the other one, and I'm definitely going to write that in my self-evaluation for the first graph, I forgot to write about increasing and decrease. So this is another way for you guys to like reflect on your knowledge and your evaluation is as you make mistakes, start including it in there. So we're here, all real numbers. So as we go to the left, the graph decreases. They use the word rapidly. Graph decreases rapidly. As we go to the right, the graph increases. It increases, but it's doing it slowly. So we're going to say that the graph increases slowly. And you're going to see that literally everything's the same. Um, they do it out of order. So it is how the order, how they asked the questions and how they listed it, because the growing part should have been at the very end. All right, what are the differences between them? There are no differences. There are no differences in the key features that I can see. You'll see why I'm saying that I can see, because it grows at a different rate. You can see here that it is growing faster than it. Because if you look at the y's, this is increasing faster, but the basic key features that I can see on the basic key features. However, it does look like ln grows faster than log. So it looks like the log just grows faster, or the ln grows faster than the log. Let's see what they say here. So if you look at that, the key features, there aren't much except the rate at which it's growing. Oh, and the rate at which it's decreasing too. It looks like it affects that as well. So, and this is what it's talking about here. The growth rate is different. So most of the key features, the graph starts lower, and that the other key features are the same. It's just the rate of growth. So you can definitely talk about that. For the second graph, I should have talked more about the rate of growth. All right. So let's look at this graphing tool, and we're gonna slide this stuff around. We're gonna slide the A around, slide the C around, slide the X around. What happens when you do this? I feel this is weird because I feel like they might have meant to do a log here. Let me check their answer because I feel like they might see flips the function. Okay. Well, let's see their tool, because those answers aren't going to make a lick of sense if we don't do it ourselves. So let's go into here. So when they're talking about C, oh, they are talking about that. Okay. So if we do this, okay. So we're going to move around with this. Changing the C, if we look at it, changes how it grows a little bit. So I'm going to talk about that first. And when it becomes negative, it looks like it flips it over on the y-axis. So this is what I meant by you can technically have it negative, but if you look here, if you have it negative, it can never be positive. All right. So the value of C affects the growth rate of the function. And when it is negative, it flips on the y-axis. So it's flipping on this y-axis when C is negative. All right. So I'm going to switch this back to 1, which should be the default. And you can see here that it looks like it also changes the x-intercept. But I think that's covered in me changing the rate at which it grows. I'm going to go back here to 1. Now I'm going to mess with the x one. Okay, so the x has a greater effect on the growth rate. So it also affects the growth rate, just it looks like it affects it more. And if it's negative, it flips it on the x-axis. Okay, so give me a second here. So I'm going to be like, the A has a greater effect on the growth rate without affecting the x-intercept. But when it is negative, it flips on the x-axis. So when it's negative, it flips on the x-axis. If you look at the c, it's interesting because the c does affect the x-intercept, but the a, which also affects the growth rate, doesn't. And we'll talk about why that is, or I imagine they'll talk about what that is, why that is a little later. But it takes a lot of like manipulating graphs. Now we're going to see what this graph does right here. All right. So using this graphing tool, now we're going to move around the x and the h. So if you see here, we're adding stuff here and we're subtracting an h value here. So let's move the h first. So the h looks like it moves the graph left and right. Everything's kind of staying the same. It just moves the graph left and right. So um, and this is the part that's kind of confusing because they are subtracting the h. So a positive makes it go to the right, but keep in mind we're subtracting the h. So it's technically a negative value. It's very confusing how they do this, but so h controls it left and right. It's the best way to kind of describe this. I don't like how they put the standard formula in here because it makes you think that if this is positive, it goes to the right. But in reality, it's like if it's negative, it goes to the right. Because even though this is a 2, it's x minus 2. So I'm just going to describe it as the h moves the graph left and right. So guess what the K is going to do? The K moves the graph up and down. So this is what I meant by you can't have negative values, but because you're changing things, in this case, you're changing the X. You're making it move to the left. So that's why I said earlier, it's like, oh, if you change the X value, then yeah, you're going to move stuff over to the left. And the reason why that is think about it this way. If you plug in, so let's say this is, oops, let's say this over here. If you're plugging in a -5 and there's also a -5 here, what's happening is this x isn't acting like a 5, it's acting like a 0 because even though you plug in -5, -5 minus -5, it's acting like a 0. So that's what I mean by um, it's not necessarily that you're changing that the x is negative because this little h kind of affects it. The k affects the up and the down. So the k um, moves the graph up and down. That's the simplest way to do it. And honestly, I don't really expect you guys to say more than that. You can talk about the x-intercepts and all of that changing. Great. But obviously, if the entire graph moves, that obviously means that the intercepts and all these other parts of the graph are also moving. So return the graphing tool to this. Okay, so now we're going to use the graphing tool, this new graphing tool right here. And we're going to change the B. So if I change the B, It's almost like how it was when I was changing the A, right? It's affecting the growth rate without changing the x-intercept. So that's interesting, and the reason why that is um, the reason. How can I describe this? The reason why that is want to remember the properties of logs. How if you have we haven't gotten into properties of logs. I don't think. Um, well, the reason why it is because there's a property of a log that says if you're changing this a is like changing the exponent. But um, again, you can learn about properties of logs later if that helps. But for right now, just you can see here that it's just changing the rate of growth. So the b changing, this is known as the base. That little b right there is known as base. Changing the base changes the rate of growth of the function, but the key features stay the same. And it makes sense that it does because when we talked about ln and log, all we were doing was changing the base. Log, like this, was log base 10. ln was just log base e. So the features changed, it's just how fast it grew change. So that's the main difference between those two. And I already kind of wrote what I was having trouble with. Um, increasing, decreasing. I had trouble listing all the changes. And that's fine, as long as you kind of understand that there's a lot that happens, so it's hard to kind of list all those changes. All right, guys. So I know I only covered like a fourth of the slides, but at least we got one activity done. I'll try to have this completed either today or tomorrow. Obviously, if you're watching this in the past, it probably should be done. And you can probably watch the next videos. All right, guys. Have a good one.